Okay, hello everybody once again. The last class, last two classes, what we saw was certain single stage amplifiers, namely a common source, and then we saw common gate and common drain, and we saw what are the advantages of these amplifiers and what are the disadvantages, and hence each of these amplifiers are good for certain specific purpose, or when you have an QRs set for some certain conditions are to be met, which doesn't which cannot be fulfilled by a single set of amplifier, then you could use cascading two stages or cascade amplifiers, even those kind of things we saw. Okay. Now today we are going to take up something different, which is known as differential amplifiers. So if you see here, this is a single stage ended output where you have a source, and you could have a source resistance or a source impedance. You have a single output out here. Okay. So what a differential signal means? Okay, there will be two terminals, and the outputs at those with respect to the ground, they will be 180 degree out of phase, right? So you have a signal this, and you have an exact replica of this signal with 180 degree phase shift on the other terminal. So there now to transmit this signal from point A to point B, I require a single wire or a single channel, and with the ground is common, so you can use the global ground. Now whereas here when I want to transmit a signal, I need to I need to use two wires. Okay, so both these inputs needs to be transmitted, say from one chip to other, or within one part of the chip to other. I will require a set of wires consisting of two wires. Okay, so that is the difference between a single and essentially these two wires will have same signal with 180 degree out of phase. Okay, that is the only difference, right? So how does it help? Like for example, you have one chip and output from one particular stage, and you have a wire which is sent to other part of the chip where you have some other component, or it could be outside the chip or within the chip. You have one line going here. So obviously in the routing you might find there are other wires also which are running. Here as an example I am saying there is a clock line which is running parallel to this for a certain distance, and you see in the clock lines there will always be some steep changes, right? 0 to 1 and 1 to 0, and although there are no capacitance which are connected between these two lines, there will be some stray capacitances, right? Because after all this is a metal, and there is an insulator in between, so it is bound to happen that certain transitions get coupled with the analog signal. So this is all noise coupling. Okay, so this cannot be eliminated for a single ended system, whereas in a differential system what happens is okay, for a differential system, what happens is I have lines going like this, right? Both the positive and the negative lines. Similar kind of noise they get injected into both these lines, and finally when you take the difference, okay, all those noise can be eliminated. Okay, because it is not that this is the same spike, right? So it gets you have a positive spike here, it's a positive spike here, although the signal is going negative out here. But this positive spike will induce a positive spike. This negative spike will induce a negative spike here. So when you take the difference finally, so all these extra noises which gets incorporated into these signals, okay, so they can be eliminated. So that is the advantage of having a differential kind of signal. Okay. So now this is a single-ended system. In which you can see that if there is any power supply noise, okay, so obviously this is a power supply line, any noise which is there in the power supply will again get incorporated as noise in the output signal, right? This is a differential signal in which this is generating the positive signal, and this is a simple way of generating an differential signal where you have the same input. Okay, two transistors are given here. The differential signals are available as inputs out here. So if you see here, the power supply is going to induce the same kind of noise in both these signals, and if you take the difference of these two signals, and they can be removed. Okay, so that is so here channel noise is being eliminated. Here the power supply noise is being removed by using an differential pair, right? This is again just a common method of generating the differential signal. You have a single-ended signal coming here. So this works like an inverting output. Okay, a certain op amps will give you both the inverting and the non-inverting output, whereas this bottom path, okay, because it is giving in the positive, and you get an in phase component. So you get out of phase component and you get an in phase component. So you can use these kind of configurations for converting single end into dual. Okay, only care you need to take it like both the amplitudes should be equal. Okay, if you have a different gain in between these two, okay, so that could induce errors into the system. So when you are using from single end to differential converters, the gain for the inverting and the non-inverting path should be equal. So if you see here, it is swinging between 3.5 to 1.5 here also. Okay, so that needs to be taken care. Okay, this is another way of doing. This is with the discrete ICs. If you see here, two ICs have been used. So this is nothing but a source follower. So you have an exact replica of it available here, and this is an inverting amplifier. So since both these resistors are of the same value, you will have an inverting output out here. So this is how we can generate a differential signal with discrete components. Okay. Okay. Is it okay till here for all of you?
Yes.
Yeah. Okay.
Yes.
Okay. So now before we study further, let's try and understand some definitions. Okay. So the first one is a common mode rejection ratio. Okay. Which is a ratio of two gains. Okay. And obviously the mod is there. On the top you have AVD. That means a gain of the difference. Like you have two inputs coming here. Okay. So when you give it to an amplifier, now you have, now for a differential amplifier, it will have two inputs A and B. So AVD stands nothing but A minus B. Okay. So how much is that at the input? What is A minus B? At the output, what is A minus B? So we are interested in only amplifying the difference of these two signals. Okay. What and then on the bottom you have a VC, which means the common mode signal. So if say for example, if the noise is there, it will be equally induced into the both the inputs, that we need to eliminate. Okay. So that is known as the common mode. So I want to keep this as low as possible, and I want to maximize the differential gain. So common mode rejection ratio is how well I am able to reject the common mode signal. Okay. Can somebody just call Mehta and ask him to mute his mic? Yeah. So this is what happens. So this ratio gives it's a very good figure of merit to define the CMMR, to define good figure of merit, and which gives the performance of differential amplifiers. Okay. Because now we need to amplify differential signal as much as possible and have as low as possible the common mode signals. Okay. So that is what another important figure of merit or performance parameter is Icmr. This stands for input common mode range. Okay, when we are going to see now different amplifier configurations, So these cannot work for the entire input of 0 to VDD. If you are making an amplifier, say plus VDD to minus VDD, or plus VSS to minus VSS, okay, so this will work fine, okay, for certain range of input signal, okay. You can't go a voltage which is close to 0 or close to VDD. So we'll see why that happens, but at time B, we just define this as an copper mode is the common mode range over which the differential amplifier continues to sense and amplify different signal with the same gain. So beyond that, if you go, the gain will reduce, there will be non-linearities which will be set in, and there will be certain issues. So I'll show a simulation of this also towards the end of the class, okay. And then you have an input offset voltage, okay, output offset voltage, that is for a differential amplifier, if both the inputs are of the same potential, right, if you are giving the same signal to both the inputs, or if the input terminals are connected together, 0 differential signal, then output should be 0, okay, output differential voltage should be 0, but due to certain mismatches in the transistor parameters, due to wiring issues and all, in all practical amplifiers, there will be some amount of output, okay, a small output, it could be the millivolt range. So that is known as V offset, okay. Now if you want to refer that offset as an input voltage, then you divide it by the differential voltage, so you get the input offset voltage, which is known as VOS, VOS in, okay. So that is, so these are some of the definitions. It may not be very clear now, but as we look at certain circuits, it will become very clear now, right. So this is one way of implementing a simple differential circuit. I have Vn, I have an this is, so two transistors. So this is Vin, which is given here, right, to this. So I have an RD coming in out here, and I have to give an 180 degree out of phase signal out here. So I get an V out here, right. So opposite signal out here. So if I take the difference between these two signals, right. So so this is one way of creating a simple differential circuit, okay. There are issues with these circuits. First of all, see M1 turn. Let me just, this is the V out common mode signal. If both the common mode signals are going high, suppose there is an both the signals are, you see, both the, first of all, both the signals have to be above the threshold voltage, right. Okay, only then these transistors will be switched on. Now, if you keep increasing the common signal, okay, so each signal you can call it as an DC signal superimposed by an AC signal, okay. So if you see here, this is the common mode signal which is applied to both these terminal as an input, okay. This is the V1 which is shown here, which is an input AC signal which is applied here. V2 I am giving an opposite signal out here, right, okay. So at the output you will find V out, which is here, which is amplified version. V out 1, with respect to this it will be inverted, with respect to the V in 2, this will be, because this is a common source amplifier. So this graph and this graph, is it okay with all of you? These two graphs, what is it?
Yes.
Okay,
yes,
VC in 1 is the bias voltage which is given here. You need to give the bias voltage also, okay, to measure these two signals, okay. Now in this, so as you increase the bias voltage, okay, so what about the DC voltages out here? Okay, they are also going to increase, okay, because if you increase, it will decrease because more ID will flow here. So this output voltage is also, that is known as the common mode signal, okay. A common mode signal is the bias voltage which is there in this particular circuit. If you increase the common mode signal in both these circuit, the voltages out here is also going to change, okay, in this particular circuit, okay. So there is an issue out here. Okay. So finally, if you keep increasing the bias voltage, right, and it could clip the output voltages out here like this, right. So that is an issue. Similarly, if you decrease it, it can turn off these transistors also. So they set the upper and the lower limit for the DC voltages out here. Okay. So you understand that. So that is known as the common mode range for this particular circuit. Okay. So minimum it has to be threshold voltage of these transistors, and maximum if you keep increasing the common mode signal, okay, this transistor will come out of saturation, right, as the current keep increasing, and the output will start getting clipped. So that is the common mode range. Okay. So that gets limited. And all the major drawback of this particular circuit is when the common mode voltage is increasing, the DC value at these 2 points, okay, they change. Okay, so you have a common mode gain also. So this kind of amplifier is rarely used. It is not used at all. Okay, we have a better topology. So is the functioning of this transistor and the drawback of this particular configuration clear to all of you? If there is any doubt, please ask me here. If I need to repeat it, I can do that. Yeah, tell me.
Yeah, please repeat advantages and disadvantages.
Okay.
And the clipping of or the clamping of that V2 signal.
Okay. So if you see here, first of all, when I increase the common mode signal, suppose I have given a DC bias of 0.8 volt initially. Now if I give instead of 0.8 volt, there will be an AC signal. This is the common mode voltage, right? So if I give if I increase the common mode voltage, is the voltage at X and Y going to change? It's going to change, right?
Yes.
Because more current will. So DC operating point will get shifted out here. So that is known as the common mode gain. Okay. So that is not desirable. Okay, for a difference amplifier. So that is one drawback. Okay. The other drawback, like if you increase, if you see here, right. So this is getting if you are increasing the common mode voltage out here, right. So the headroom available here will be, so it will already suppose you are giving very low common mode voltage here, so it will get already a very high voltage out here. Okay, already large current is flowing here, so this will be close to VDD. So it is going to get clipped, right here.
Okay.
So that is an issue out here. While this is getting clipped, this will not get clipped. Whereas when this is going high, this will get clipped. Okay. The higher common voltage, they are getting clipped at different instances, right? So all this is an issue with this kind of amplifiers. Okay. Is it okay now?
Sir, when Vin is low, then Vout will be Vout common mode will be more.
Vin is low,
then Vout common mode will be high.
No, a common.
Or is it opposite?
No, common mode differential signal. We are talking common mode means when both the signals together, when they are going high, okay, the common mode signal will get close to VDD. Is it okay? Is this understood? If I increase the common mode, okay, the DC operating point will get close to VDD.
No, but
no, it will come. It will come. Okay, sorry.
Down.
It will come down. It will come down. Yeah, you're correct. Right. So that can happen. So the signals can get if you give a small VDD, the signals can get clipped. Okay, if the common voltage is low. Same happens in the other way around also. Okay, if you keep a very high voltage, right, with small increase in voltage, the current cannot increase further. So it will get clipped at the bottom portion also. These transistors can happen in the other direction also. So these are some issues with simple differential circuit. So practically we have all the differential amplifiers will look something like this. Okay. So in today's class, okay, we are going to analyze a differential amplifier considering an ideal current source which is placed here, right? So in the next class, we will replace this ideal current source with a MOS current source and see what are the changes which would happen to the analysis which we done. Okay. So when you put a constant current source out here, right, it is known as current stealing phenomena, because as you keep increasing the Vin out here, right, if I keep increasing Vin, right, the current which is going to the tail is fixed, right. So it will automatically result in a decrease in current out here. So the sum total of these two currents is always ISS, right. So if you see here, this current is fixed because this is an ideal current source. So if you increase, so this is the differential signal out here first of all. Okay. So if I keep increasing both the voltages together, will the operating point shift? Anybody? If I keep increasing pardon?
They both will draw equal currents, and output will be VDD minus ISS by 2 into R.
Correct. See, in this particular configuration, as long as this transistor is in saturation, okay. So obviously, first and foremost is that we are assuming. Yeah, just give me 30 seconds. I'll complete this and I'll take the question. Okay. First of all, there is a constant current which is flowing here. We are imposing a condition where both these transistors will be in saturation. Okay, so that means the input common mode range will be limited. And what are those limits? We will see subsequently. Presently, let me tell you that both these transistors are in saturation. So given that condition, when both the signals increase or decrease by the same amount, okay, the output voltage will not change. Okay. Because both the branches will have ISS by 2 current as long as Vin is equal to Vin2. So there is no common mode signal difference, unlike which happened here. Okay, so the common mode gain is going to be 0 in this particular case. Okay, is it okay with all of you? Yeah, somebody had a doubt. Can you ask me that?
And so that is what I was telling you, in saturation mode. As the current through RD1 is will be constant, so there will be no change in V out.
Correct.
Even if you are increasing the V, that is what I.
Correct. So as long as Vin and V2 are increasing at the same, both are equal. Okay. Obviously RD1 is equal to RD2, and M1 is same, has got the same parameters as that of M2. So the width and length and all has to be same. We'll see because obviously these are all ideal cases, and there will be certain mismatches when they get fabricated. Okay, there will be some difference in RD1, R2, M1, M2 and all. What that would happen, that we will see again in the subsequent class. Okay, as of now we are assuming that both these resistances are perfectly matched to each other, and M1 and M2 are also perfectly matched to each other. This is an ideal current source. Okay, when I say ideal current source, okay, irrespective of whatever happens here, right, there is no R0 out in parallel to this. Okay, so constant current is flowing here. Okay, so all this ideal will replace with real world devices in the subsequent classes. So differential amplifier will be studying for three different classes. It's very important topic. Okay, now we talk about. Now we talked about the common mode signal. Let's speak about the differential signal. So initially, see, the differential signal is 0 out here. Okay, differential signal 0 doesn't mean both the signals are 0 here. Okay, there is some common mode signal available here. Okay, C out. That is that common biasing voltage of both these terminals. Okay, that has to be greater than Vt to ensure that these transistors are saturation. We are assuming that is there here. Okay, that is available out here, right? And then Vin minus V2. I mean, only Vn is increasing with respect to V2. This is increasing. Okay, this voltage is increasing. As this voltage Vin minus V1 increases, okay, what happens? What happens to the current? This more and more current is going to flow in this particular circuit. Okay, and finally, what will happen? Okay, this V out one. Okay, more current is going to flow here. I think, did I write an equation? No. Okay. Yeah, okay. So more and more current will flow here, right? And finally, the entire current will flow here and no current will flow here. Will that condition happen? If I keep increasing Vn, we will reach a situation where the entire ISS will flow only in this branch. It will not flow here, right? In that case, what will be the output voltage? It will be VDD. This particular voltage, okay, will be VDD minus ID RSS. So is this one particular graph understood from initially? Okay. Similarly, if now Vin is rising with respect to Vin, it will be a negative voltage and it will come here. Okay, it will come to once this is not there is no current flow here, then this output voltage will be a VDD here, right? Because there is no IR drop here. So this will be VDD. So if you see here, as the differential voltage is from 0, it is going high. After some point, okay, V out 1 will come from VDD to VDD minus IDRSS. The center point is VDD minus IDRSS by 2. So is this three ranges, this is the common mode voltage. Differential voltage is increasing out here, Vin, right? More current will flow here. Initially, okay, if I say if this is sufficiently large, then no current is flowing here, so it will be V out. Then slowly it will come to a point where both these voltages are equal. Then equal current will flow here. It will be VDD minus RDISS by 2. And then if I keep increasing this voltage, then it will come to VDD minus IDRS. So this is the kind of curve. Is this curve understood? It's a very important aspect. If you have not understand, we can discuss it once again. If you understand, I'll explain the next graph. Okay. So is this understood by all of you?
Sir, right. Second thing, what you told, like when all the currents through M2 transistors. So how the graph will be look like here?
See, this is right. Vin. Okay. Initially, let's take just the positive portion of it. Okay. Let's talk about only the positive. Both the input voltages are same. So ISS by 2 will flow here. ISS by 2 will flow here. What will be the output voltage? Both the output voltages will be okay. VDD minus RD RSS by 2. Now, as this voltage is increasing, right? More and more current will flow here. Right, more and more current will flow here.
Vn1.
So
Vn1,
yeah,
you were talking about Vn1.
This is V out 1. Yeah, V out 1 is this curve. Okay, the top, this curve which is coming down is V out 1. It's written V out 1 here. Right. So that voltage will keep coming down, and it will ultimately reach VDD minus RDRS. This is the value. If you see here, it will come to that value. Since this current is increasing, the current is decreasing here. So this voltage will increase. So this voltage will increase and reach at VDD. So similarly, in the negative cycle, it happens the other way around. Is it okay now with all of you? So maximum range of voltage you will see here is from VDD minus RD RSS to VDD. So this is the range of voltage. Is it okay?
Yes.
Yeah. Okay.
So
Now,
one question.
yeah, sure.
Sorry.
Sure.
Yeah, sir. In this case, since you are saying that both when we are shifting, increasing Vin1 and Vin2 together, since we have that constant current source ISS, the DC operating point will not be shifted.
Correct.
So there will not be that clipping happening.
No. As long as these transistors are in saturation, and there will be some limitations on the range of voltages here. Okay. As long as these transistors are in saturation, same current will continue to flow.
Okay.
Right?
Okay.
What are those DC restrictions? We will see that also. Right?
Okay. Yeah.
Now, this graph below shows the difference in voltage between X and Y. Okay? V out 1 minus V out 2. Okay? So this VDD gets a minus. So from plus RDISS to it will go to minus RDISS. Right? V out minus V in. Is this graph understood? Right? When both the input signals are same, I have 0 voltage out here. Right? Now V in is increasing, so V out will decrease. right? So this will with respect to, and this will increase, hence it is going below, and maximum this is going to be VDD minus VDD minus RDRS. This is going to be by that time this is going to be VDD. So if I do the subtraction, VDVD gets cancelled. So if I take the potential between these 2 points, this is how the graph will look like. Is this bottom graph clear to all of you? Right? So
sir, one doubt, sir.
Yeah, tell me.
Sir, when we are increasing Vin, then sir, I am thinking like this, like ID, that is GM into Vin is increasing. So as GM into Vin is increasing, so the current through RD1 is increasing. Is that correct, sir?
Yes.
So as a
Yeah, tell me. Your voice is breaking. Is there an issue with my headphone or?
hello.
You are audible, sir.
Yeah, Ashutosh, there's an issue with your mic.
Hello.
Yeah.
Yeah, sir, I am telling you, if Vin is increasing, sir, with the GM into Vin, that is the ID inside the current flowing inside the device is increasing. So that is causing the current through RD1 to increase.
Correct.
And as the RD1 is increasing, so the V out one is decreasing. So
Correct. Correct.
Is that what is happening?
That is what is happening. Right? Exactly like what happened in the CS amplifier. Okay. So so this is the circuit. Okay.
Sir,
Yeah, tell me.
sir, I am not getting this above graph left portion, negative portion.
Negative portion. Okay.
Uh,
So suppose V in minus V2 is negative. Okay, that means V in is greater. That means more current will flow here. Right?
Okay.
Less current will flow here. Right?
Okay.
If less current is flowing here, it will go high, right? This will go high. V out one.
Okay.
Right?
So it can reach maximum.
Can we move to the next? Okay. So let me move here.
Sir, you were discussing it was ongoing.
What was I discussing?
Left side part of this curve.
Okay. So on the left hand side, when this signal is low with respect to this, here there is lesser current. So this will slowly go and hit out at VDD. Okay. And simultaneously V out 2 will keep coming down because more current is flowing here. So this voltage will keep coming down out here. Is it okay?
So, sir, y-axis is representing voltage only, or it is representing
Voltage.
okay. Okay, so sir, I didn't understand why
this current is V out current, V out voltage. This curve is V out 2 voltage. This is V out 1 voltage. And x-axis is V in minus V in 1 minus V in 2.
Okay. That means this one which is going upside from left to right, this is VO1, V out 1.
This which is rising is V out 2. It's written here V out 2, right?
Okay.
Right? When V in this increases, this will decrease. So this is coming down. Yeah.
But sir, this V out 2 is going till VDD minus RD ISS, but V out 1 is going till VDD. It should not go till VDD minus.
VDD minus RD RS by 2 is the midline here.
No. VDD minus RD ISS.
This is the negative most. This is also will come to that value. Right? When no current is flowing, it will be VDD. Okay. The other condition is ISS is flowing. Full ISS is flowing. It cannot go more than that.
Okay.
So in that, this is the minimum limit.
Okay.
Okay. Is it okay with all of you? Okay. So we move ahead. These are some of the current equations. Okay. So I think I mentioned it in the morning class also. This is Kn dash. Okay. Kn is Kn dash into W by L. Right. Kn is mu n Cox WL. Right. So these don't confuse with these thing. Okay. So somewhere we will see VGS minus VTH is written VOV square. Okay. So this is also written, and in some places you will also find beta, which is this entire thing. That half is also taken care of. This half also is also taken care of. So we just write these. Okay. So Kn and Kn prime, beta, these things you need to remember. VOV is overdrive voltage. Okay. Here we have not yet analyzed what will be these output voltages. Okay. At which this entire what is the amount of differential voltage which will be required, okay, for this to make complete swing, that we have not yet analyzed. We will see that. Okay. Now if you see here, okay, this is ID1 plus ID2 is ISS, that is one equation. Okay, this is the current equation, VGS minus VTS square, okay, is equal to ID divided by, so if I just write an VGS, this will be square root plus VT, right? Now if I take the difference of these two signals, V in minus, so that VTH will go, so I'll get this equation out here. So if I square these things, so obviously this square plus this square, so that square root will go, and 2 ID1 plus ID2 will be there, so that ID1 plus ID2 will become ISS. Okay, so A square plus B square, that together will become ISS, 2 ISS, right, plus that minus 2 AB. Okay, so that 2 AB thing, okay, which will still be under the root out here, right? Is it understood how this we reach this equation? A square B square, okay, this root will go, right? So you will have 2 this ID1 plus ID2 will become ISS, right, minus 2 ABC, right? So that 2 is here, right, and in the denominator, since they are the same thing, that will come out of the root, so that has been taken common here. In the numerator you have 2 root ID1 and ID2, they are both in the root only, right? So you get this equation, right? So now these things have been brought here, and this IS is also brought here. Okay, again you do one more square of that, right? So this becomes 4 ID1 plus ID square, right? And that can be written as ID1. So I am not writing this. Okay, this is written A plus B square minus A minus B square, right? So now A plus B square is nothing but ISS square minus ID1 minus ID2 square, right? Now this portion I am retaining out here, okay, and ID1 plus ID square, this I square is also I am retaining out here, and from here, okay, this has been written here. So if you write that, you will get ID1 minus I2 from these equations. If you solve, this is the equation which I get the difference in current voltage. Okay, so this equation. So this is just, okay, you got it. What we have done, we have written the equation for VGS, okay, V in minus V2. So I have taken the difference of both these two. I have done a square of that. Okay, if I do a square, ID1 plus ID2, which is coming from the A square plus B square terms, I am writing as ISS, and minus 2 ABC term will come here. So I am leaving that root term here, and I am bringing this ISS out here. Okay, and then I leave this aside for time being. Now I am writing 4 ID1 plus ID2 is A plus B square minus A minus B square, right? A plus B square minus AB square will be 4 ABC, right? 4AB. 4AB is equal to A plus B square minus A minus B square. So I am writing that quadratic equation. Now A plus B square is ISS square, right, minus ID1 minus ID2. Okay, so I am getting one equation out here. Okay, so this ISS square, right, I am going to square this again once again out here, right? So I'll get 4 ID, right? So and that I am going to replace here. So I am going to put a square of this here. So this ISS square and this ISS square will get cancelled. This is A plus B square. So that I am expanding out here. So I'll get ID1 minus ID square here. Is it understood? Certain steps are not written here, but I think it's just a plain mathematics, right? Okay, so you got it. What I'm doing is I'm squaring this. Okay, so so when I do a square, what I will get? ISS square I will get. I'll get square of this and 2ABC, right? So square of this I have written out here. 2ABC part I have written it here. This ISS square I am equating it with this now. So this ISS square and the square which I get, they get cancelled. So I get an equation ID1 minus I get this equation. Okay. Now what is the importance of this equation is here, right?
Excuse me, sir.
Yeah. Tell me.
Which two equations did you equate?
See, I have 4 ID1, I2 out here, right? Okay. So this is the equation
Yes,
1.
Right.
I got one equation out here. Right?
Okay, sir.
If I expand this, if I do a square of this, right? This I will get.
Right.
This and this is same, right? So
Right,
I am going to equate this portion with the square of this portion. Okay.
Okay.
Now when I am doing here, I have this square, okay, and this square which will get cancelled out. Is it okay?
Okay, sir.
Right?
Okay.
If
Right.
they get cancelled out, what is going to remain? This is going to remain on one side, right? Here. Okay, this minus is there. So I am going to get square of this. Okay.
Okay, sir.
But since
Right,
this
right.
negative I am writing it positive, I will get a square of that. So I am putting a negative out here and a square of this portion, and that minus 2AB. So minus will become plus, right? 2 this gets cancelled. Mu and Cox is available. The rest of the terms are available here.
Yes, sir. I get it. Thank you.
Okay. So this is how. Okay. Now this is the equation which I get. Okay. Now if I differentiate with this ID with small v in, I get the value of GM. So I get this particular equation. Okay. Now in this equation, if you see here, when v in 1 is equal to v2, GM is maximum, and as you keep increasing the differences, the gain decreases. So that means for a differential amplifier, initially when the two inputs are close to each other, right, a small change in voltage, it will have very high GM. Okay, as they keep as the difference between these two signals keep increasing, the gain will decrease. Okay, is it okay? This curve. So this is the transconductance of an differential amplifier. If you see, when we learnt about a simple MOS transistor, this was the transconductance. From here to here, nothing has changed. Only thing is, here I had ID there. Here it has become actually ISS by 2. Okay, because only half the current is flowing in this circuit when both the input signals are same. Okay, and that is the condition for max GM. So that 2 and 2 has got cancelled. Actually, these two signal formulas are actually the same. Okay, instead of ID, I have replaced it by ISS by 2. Okay, so is this condition understood? When will there be maximum? If you see here, these are the current curves. Okay, 0, it will go up to maximum ISS. Okay, these currents. Okay, in this transistor, right, and this is the maximum GM condition. The maximum GM will be here. So we are going to operate close to small different signals. So we can say the GM of this is going to be this mu and Cox root, which is the same GM which we had learnt earlier. Is it okay with all of you? Okay. So let me move forward here. Right. Now the differential gain, okay, is V out minus V out 2. If I take the difference between here, it is an RD into delta ID. Okay, so delta ID is now GM we found out. Okay, so delta V in. So the gain is again GMRD. Okay, like in the case of common source amplifier. Okay, so the gain is here. Okay, only thing is ID got replaced by ISS by 2, so that 2 is not there. otherwise it is the same gain as that of a common source amplifier. Okay, is it okay for all of you?
Yes, sir.
Yeah, okay. Now we want to find out a condition where what is this voltage at which the gain becomes 0. Okay, what is that this condition where the gain becomes 0. Okay, so in this equation for GM, right, if I put an 0 out here, right, if I try to compute by putting this value as 0, right, I can get Vin minus V2. What is the value for Vin minus V2? Okay, that is delta Vin. Okay, for which I can find out that value. Okay, so that will, so this entire denominator will become 0. So this will be there. So you take a root of this. So I will get this value. That means when the difference voltage is this much, the differential gain will become 0. That is 2 root ISS mu and Cox WL. So this is the differential voltage at which the differential gain will become 0. So if I go back to my earlier stage, this is this voltage and this voltage. Okay, when the difference voltage, this voltage becomes equal to this value 2 ISS by mu and Cox. Okay, then if this voltage, then the entire ISS will flow here and this voltage will come to 0. Right. Similarly, if this voltage is increased is more by VEN1 by this much amount, then the entire ISS will flow in this branch and the voltage will be 0. So so this is the,
Sir, your pointer is not visible.
okay, sorry.
Sir, you mean to say that like if ISS flows in one side, then another side of the transistor will be off. MOSFET will be off. Hello, sir.
Yeah. Just one sec. Let me. Yeah. Okay. Yeah. Tell me.
Yes, sir. Like you mean to say that that ISS flows in one side, that means another side of the MOSFET will be off.
Yeah, it will be off. There will be no current there. Right?
Oh.
So
Instead of ISS by only ISS is flowing.
Correct. So if I go back here, like here, if I go back to this my initial circuit, initially there is no difference voltage. Okay. Initially both the input voltages have got a common voltage, so that these transistors are in saturation region. So I have a common voltage here, right? ISS by 2 and ISS 2 is flowing here. So in that case I have max GM value also, right? So if I go here, this is the GM value, max GM I have. Okay. Then subsequently, as I keep increasing the voltage, okay, difference voltage, entire current will flow in M1. This will get there will be no current out here, and this voltage will come to VDD minus. And what is this particular voltage? This is the range, useful range for my differential. After this, if I keep increasing the difference voltage also, I don't get any change in the output. So that is not my useful range. My useful range is from here to here itself. So what is that range? That range has been computed here as this. Is it okay with all of you till here? Is it okay?
Yes.
Okay, sir.
Yes.
Okay. Now there are two differential gains. Okay. One is V out minus V. This is the difference voltage if there is a difference in input voltage. Okay. So that is how much is that? If you see what we have learnt is, okay, that is going to be GMRD. Okay, that is one. And what about this voltage? When this is the difference voltage, and this I guess it should have been common. Okay, single ended. Okay, if it is single ended, that means I am taking output only from this place. I am not taking from this place. This is I am taking the difference between these two. And what about single ended? Okay, so that is there. So if I revisit my common stage stage with source degeneration. Okay, if I talk about this particular amplifier. Okay, so this is Vin. Okay, we'll see this derivation and we'll use this formula again for that to understand the differential pair. Okay, so here if you see here the difference here. Okay, the differential gain will be twice that of the signal single ended. Okay, if I take the output here with respect to the ground. Okay, and if I take output, because you have a negative signal coming here, so once you take the potential between the differential pair outputs and the single ended outputs, the differential output will have again twice that of the single ended. Okay, now we are trying to first we'll revisit this particular derivation and we'll go to the derivation of the differential amplifier, right? So if you see, this is the common source amplifier with RS. Okay, there is no bypass capacitance. Remember, there is an RS. Let's try out find out. Okay, so Vin is equal to VGS plus ID RS. Okay, that is one equation. Then Vin is equal to ID is GM into VGS. Okay, GM into VGS. Now, so I can take VGS common out here. Right, so this becomes 1 plus GM RS. Okay, so now if you see V out is ID RD. V out will be ID RD, right? If I substitute that out here, right? VGS here ID as an GM VGS. So here ID is GM VGS. Okay, I have done that. Now this is V out and this is V in. Now if I divide this, I get minus GM RD by 1 plus GM RS. So minus RD divided by 1 by GM plus RD. So this is the equation which we got for the gain. Okay. Till now, then we talked about, since RS is going to be much higher than 1 by GM, we neglected that there and we wrote the GMS minus RD by RS. But here we are not going to neglect this. We are going to take this into consideration. Is this okay with all of you?
Sir,
yeah.
So one small doubt.
Yeah.
In this equation, RD, we are neglecting. We are taking VDD equal to 0. Sir? So this is a DC voltage.
Yeah, DC voltage is because this is AC equivalent, right? So all the DC sources we are putting it to 0.
Yeah, that's why VDD is to 0. So it is V out is equal to ID into RD, right?
Correct.
For that loop.
Yeah. Correct.
So that might be due to that current flow direction.
Pardon?
That minus you have put now for minus VGS.
Yes.
It is for the current flow direction.
Yeah, that's catering for the current flow direction, right? Because it is going to flow like this, right? In fact, it is going to be minus ID here also. So that is good.
Because V out plus ID is equal to 0, V out equal to minus ID.
Yeah.
Because it flows in the anti-clockwise direction.
Yeah, correct. So if I have a load here, it is going to actually you have RD and then ground, and this current is going to come like this, right? So that is why there has to be one negative. Let me put it there. Yeah, is this okay with all of you, this equation?
Sir, I don't got the reason for this minus sign. Why you put the minus?
Okay, let me explain to you. Okay, first let's see, if Vin increases, what happens? More current will flow and this voltage will come low. V out will go low.
Yes, yes. So this
Right,
is because the same thing we seen inverting kind of output.
Correct. So same, we are talking about the same thing, and that is
Okay,
why
okay.
this is going to be negative. But in small signal analysis, okay, that is one understanding. In small signal analysis, I have not connected here. So there will be one RD here, right? right? Now since ID I have taken it like this, okay, V out is on the top, so this will be minus ID RD, right? V out, because ID is going to flow like this, right? And this I am taking at plus V out, right? So this negative has come from there.
So, sir, is this like this, or there is there is a branch, is it current coming from RD?
No, this is the small
Because
signal.
we have made
in the
made
small
something
signal
different,
in the small signal I have put this as ground, right?
Okay. Okay.
Right? All the DC
Okay.
voltages will be put to ground. So current will flow like this now, ID. Is it okay? Why that negative has come?
Okay, got it. Plus minus, so
Yeah.
minus sign is okay.
Okay. So now so remember this equation, right? Now I am talking about differential mode response. Okay, I am giving so this transistor I am making a small signal equivalent of this. Okay, so this will get removed. Okay, so this is an open circuit. Okay, voltages will be done short circuit. So this is an current circuit. So this I will remove for the small signal. I will remove this, and this transistor. Okay, this is here it is grounded now. I am giving only signal here and trying to find out what will be the voltage at Vx and Vy, okay, because of this signal. So I have given a differential signal out here. So this is RD. Okay, now what is the resistance as seen into the what is this source of this NMOS transistor? It is 1 by Gm. We did this in the last class, right? When I talked about the current sources, right, different loads, right, we did this derivation, right? When you are looking into the source of an NMOS transistor, what will be the impedance seen? 1 by Gm. Do you remember this?
Yes.
We did this derivation in the last class, okay? So this becomes 1 by Gm, okay? The resistance as seen, okay, into the source of a transistor with the gate being grounded. When I look into this, it will be 1 by Gm, right? So this is this. Now it has become like this, okay? So now if I try to find out the gain, it will be minus RD divided by 1 by Gm1 plus 1 by Gm2. Actually, this RS has become 1 by Gm2. Is this thing clear to all of you? This much?
Yes.
Yeah. Okay. Now
Yes.
this is what I have found out. What is the small signal variation at point X with small signal given at here? Okay. So this is the different signal. Okay. I am assuming the entire different signal is given here, and I am grounding it here. Okay. So just for simplification, or I have to give VDD by different signal half here, half here. It doesn't matter. If I give full here and ground here also, I will get the same result. So I am giving the full differential signal here. Okay, V in 1. Now in this case, V in is the differential signal. Okay. Now I am trying to find out this signal. I am giving a signal here. What is the output voltage out here? Okay. What will be the output voltage here? Okay. Now for that. This is going to act like a constant current source, right? GMB that is going to into the base of this transistor. So this is the current source. Okay, so that current source GMB1 can be modeled as this is a current source that can be modeled as a voltage source in series with a resistance. Okay, so this voltage will become V1. And RT will become 1 by Gm1. Is it okay? What this transformation means? Okay. Now I am talking. This part is remaining like this. I am trying to find out what will be the voltage here. Initially, I tried to find out if I am giving a different signal, what is happening here, right? Now I am trying to find out if I am giving here, what is going to happen here, and then I am going to take the difference of these to get the differential gain. Okay. So that is the approach. So first I did that. Now I am talking about this is the current source. Okay. Now I have put it in the top direction like this here, because this is actually going to be from top to bottom. But for this transistors, it is going to be from bottom to top. Okay, like this, right? So I have written GMVN. Okay. So this is the current source. this current source has been modeled as a voltage source. Okay, so voltage, while doing a transformation from voltage to current source, okay, I put this Vt, okay, Vt will be equal to V1 and RT will be equal to 1 by GM1. Okay, so this is standard what you see in electrical science, voltage to current transformation. So this has been done out here, right? Now if I write an equation out here, VGS2, okay, minus VGS2, because this is ground here, right? So this will be minus ID GM1, okay, plus VGS1, okay, because this is the voltage, Vt is VGS1, right? And this current is now flowing like this, right? It is going to flow like this, or depending on the current direction which you take, you write ID1 and this value of RD. Now I am assuming an ID is flowing like this. Okay, so let me assume an ID is flowing from top to bottom. Okay, so if ID is now flowing from top to bottom, I have to write VGS. Okay, so here if you see here, it is grounded here, so I have taken minus IGS1 ID into GM1. This is the resistance. Okay, this resistance and this voltage. This voltage is this voltage is Vin1. So I write VGS1, right? So I get an just ID1 by now this current also, okay, this current ID this is also this also acts like a current source, right? So that current is written by an ID by VGS is the current. If I consider this as a current source, okay, this is only summation of these three voltages. Okay, now that VGS I can write by ID by GM2, right? Because an ID is GM2 VGS. Okay, so that I have replaced out here. I have written here. I don't instead of VGS I have written by ID by GM2 out here, right? So I get one more equation from which VGS1 I get this particular equation, and V out, okay, that is ID RD2. Okay, with that if I try to find out the gain out here, right? So this is the gain I get, minus 2 RD by 1 by GM by plus 1 by 2 RT. Okay, now if I am here RD by 1 by GM2, I get the same thing which I got for this. Now if I take the differential gain, I do a subtraction of those two, so I will get 2 RD, right? So GM1 by GM2. Now if I assume both these things are GM1 and GM2, both the transistors to be of the same size, then I will get GMRD as the gain, differential gain. Is this derivation clear to all of you, what I have done?
Sir, one question, like from the top, like minus VGS2 we have converted into ID by GM2. Yeah. So that again in the same direction, so it should be minus ID by GM2. Like, how did you take in the ID direction here?
You can just try see you follow any one convention. Okay, either you write GM current, now assuming current is going to flow like this. Okay, if that be the case, okay, then in this particular case, okay, I have taken an ID is going to flow like this. So this voltage, since current is going to flow ID1, ID1 I have okay, this current has been taken in the opposite direction out here. So that is why I have put a negative out here. So VGS2, because this is positive, this is ground, I have taken a negative out here. Okay, so accordingly the way you decide the current, once you take the current in a particular direction, you can write this equation accordingly. It doesn't matter.
So second line, sir, when you are converting minus VGS2 with the ID, so okay, like ID that VGS2 will be 1 by GM2. So that ID into 1 by GM2 with that resistor, right? So that will be minus ID by GM2 equal to minus ID by GM1, right?
No. So in that case, VGS is negative, right? So that negative is good. You can do this. Okay, you just try to make a small. Maybe I should have made it. You can draw a small signal for this, and then accordingly mark the currents. Okay, you will reach at this place, same place. Okay, doesn't matter. So if you see here, this is the gain at this point with respect to this input. I am assuming the entire differential input is given only one end. This is the gain at y point. Okay, so if I take Vx minus Vy, I'll get a differential gain as GMRD. Okay, so again you came to the same what we learnt about the CS amplifier also. We learned the same thing, right? The gain is GMRD, right? Here also the gain of a differential amplifier is also a GMRD. But the important thing to remember out here is, of all these derivations, okay, the important thing what is to be remembered here is, whenever I talk about GM, it is not ISS but ISS by 2. Is it okay with all of you? Okay, remember that when I compute GM, right? So if you see here, when I computed GM, right, here it is ISS by this is ISS in this particular equation. I am talking ISS with respect to this equation. Okay, if I am writing this, I am using this equation, then this is ISS, full ISS, right? If I am using this particular equation of MOSFET, okay, then I drain is ISS by 2. You need to remember that. Okay, is it okay with all of you? Okay, so these are all some of the derivations.
Sir,
Yeah, when we are considering that for one single stage, then when we consider GM, it is ISS only, right? Not ISS by 2. For example, that Vy by Vin 1 when we are considering.
No. Here also, see, to compute the GM, right, of a transistor, I have to take ISS by 2. Okay, so the single end gain will be minus GM by 2 RD, right? GM by RD. Okay, this is small GM of a transistor. Okay, and the DC current flowing in this transistor, to compute this GM, using this formula, ID is ISS by 2. Okay, this GM is for the differential amplifier GM, capital G. Here I am talking about small g here.
Okay, so when we are considering one single-ended gain for one single line, at that time we are considering that ISS by 2 is the current flowing through it, not
correct.
ISS.
Not ISS.
Okay.
Right?
Okay. Yes.
So this is the single-ended gains. Okay. Now here I will have a negative signal. I will have a positive signal here. Each of the gain will be GM by 2. Right. It will be negative here. It will be positive out here. Right. Now if I compare a differential gain of an amplifier with that of an CS amplifier, if the same current source drives, okay, in each transistor, then differential amplifier has 1 by root 2 times of the transistor. So differential gain reduces by a factor of 1 by 2. Right? If both amplifiers have W by L, same load, we can say that in differential amplifier the gain reduces by a factor of 1 by root 2. Right? If you assume that the same ISS is used there in the CS stage. Okay, because in differential amplifier only ISS by 2 flows into each of the branches. Okay, so that is why because there is a root there, so GM goes into the root. Okay, right? So in a differential amplifier, when I am speaking ISS is the total current. So in each of the branch there will be only half of that which will be going. Okay, now to make life simple till here, okay, we saw detailed derivations, but there are way we can approach this problem in a simplified manner. Okay, now if you see here, what is this voltage? Okay, I into plus IR. Okay, so I can assuming this to be an suppose I am giving an assuming this is as an simple on resistor. I can write I as IR. Okay, and then VP is IN2 let me think what I have done here. Okay, Now both these, okay, both these transistors, if I consider as resistances, okay, simple resistances, here from here to here I considered as R, here to here I consider it as R. I am giving V in voltage here, I am giving V into voltage here. So what will be this voltage out here? V. Is it understood what I am trying to say? I have replaced this transistor by a simple resistance R. Here also I am replaced it by a simple resistance R. Okay. So both are resistances. Okay. Now if I have to find out what I am giving a V1 voltage here, V in 1, I am giving a V into voltage here. I am trying to find out what will be the potential here, right? So the potential here will be VE2 plus IR drop here, right? So what will be the current flowing? The V in 1 is here, V in 2 is here. So difference V in minus 1 2R, and then there is a 2R resistance in this circuit. So denominator 2R, so into R. So that is the drop here. So this voltage VP will be given as, okay, V in 1 plus V in 2 by 2. Is it okay? Is it okay or is it confusing? Am I audible first of all?
Yes, sir.
Yes.
Yeah. What I have done is, okay, I am put one resistance here, one resistance here, right? Instead of these two transistors, okay, I have put one resistance here, one resistance here. What will be the current flowing in that resistor? V in 1 minus V in 2 divided by 2R, right? That is the current which will be flowing there, right? Both I have put just two resistances there, okay, normal on resistance. So that is the current which is going to flow here, right? And what will be the voltage at P? This voltage plus that IR drop. So because this is I am assuming this is higher, this is lower. So this voltage at P will be this voltage plus this voltage. So I have done. So I have got here. So if you see here, okay, what does this equation mean, right? So this VP, okay, is always going to remain constant as long as the common volt signal is going to be same, right? So for all, so this voltage is not going to change as long as the common voltage is same. Okay, so that means this is a kind of for DC signals. Okay, for the DC signal, this is going to be equipotential, right? So when we do the small signal analysis, okay, for differential gain, since this point is not going to change with DC signal, I can put a ground here. Okay, so this is known as virtual ground. Is it understood? Right? These two transistors, yeah.
So in this equation, in the first equation, that is Vp is equal to V into plus IR, we are considering the right loop, consisting of V into R
this
and
loop, this loop,
Vp.
this loop.
Yes,
this
right,
win
yes.
and this.
And in the in the second equation, sir, we are taking the entire thing. Like,
we are replacing
R,
this value of I. No, we are just replacing the value of I here.
For calculating that, I, sir, we are considering the entire thing, sir, from V in 2 to R, then V in 1.
Yeah, correct.
Then we are getting the I value.
Correct.
But in that case, sir, we are not taking VP into picture for calculating I, because VP is there, no?
No, VP is just just a point here. As of now, so they are of the same potential. We are trying to find out that potential.
Yes, right? That is a common point between these.
Yeah, common point. So essentially, okay, this can be considered as a virtual ground. Okay, because with the DC signals, the potential remains same. So our circuit like this, okay, gets simplified like this now. Okay, for analysis, this is known as half circuit. Okay, once so now this V out will be a GM into RD. This V out will be again a GM into RD, right? So it is simple, and the difference will be GM into RD. So instead of this complex method of arriving at that formula, okay, GM by 2 RD or whatever, so we can use an half circuit out here. Right, this is known as a half circuit analysis. So whenever a differential amplifier needs to be analyzed, you can apply an virtual ground here, and we can find out the DC, AC. This is the AC kind of equivalent we can do. So this we can split this and do the analysis separately, and then we can just double the gain. Okay, so this is known as half circuit. Okay, so this is like V in is given here. This is again showing. So there won't be any voltage change out here. So this gain will be GM into RD. This will be also GM into RD, right? And then the differential gain will be because now when I am talking about the half signal, I am going to take only half the differential voltage here and half the differential voltage here, right? So this will be VID by 2. So VID by 2, VID by 2, right? When I make a half circuit, I also put the so VCM is going to common here. Half the signal will be here, half the signal will be here. Okay, when I make an half circuit, we have to assume that since we are splitting these two, only half the differential signal will bring here, half the differential signal we will take it on the other side. It will be VID by 2. Okay, that 2 is missing out here. Okay, so this has got missed. So it will be 2. So ID. So this will be the gain. Okay, now this GM corresponds to, remember, ISS by 2 when we compute that. Okay, so this is the two gains, GMRD, ID by 2. So total differential gain will be GMRD again. The differential gain will be GMRD. Right? Is it okay with all of you?
Can you please go back to the previous slide?
Yeah. Here? Here?
No, the next one.
Yeah.
Yeah, here itself.
Yeah.
The half circuit over here, when we are considering the circuit on the left with the ISS.
Okay.
The input voltages are same in both the circuits, right?
Yeah.
V in one, V in one.
Yeah, minus.
And then, yeah, right. And then on the next slide, I could not figure out the concept of half circuit. You were just explaining that it gets divided by half. That is what I'm confused about.
The difference voltage. Okay, when I consider the half the circuit, I am putting a virtual ground, right? And since I am putting a virtual ground and treating only half part of the circuit, I will assume that only VID by 2. Okay, VID is nothing but V in 1 minus V in 2. Okay, so half the voltage is available, half the voltage is available here.
Okay, sir.
Okay. So this voltage also I am splitting it into 2. So when I do the analysis, I will be doing it like this. Okay. So this is known as a differential. Okay. Now, so this is again. Now yeah. Tell me.
So can we go 2 slides back?
Yeah.
One more. Yeah. So for the first equation, Vp is equal to Vi into plus IR. If we'll consider this loop
only this
from the
loop.
D2 side, right, from the D2 side V into then coming to V2 then to the point P, then it should be V into minus
IR.
minus V, right?
Yeah.
Minus.
Yeah, I am taking it as plus IR because I am assuming V in 1 is greater and the current is flowing from V in 1 to V in 2. Okay.
Okay.
Okay, I am considering the current is flowing from the left to right. Okay.
Okay.
And that there I have replaced this current like that. That's the reason I have replaced the current like that.
Okay, got it.
Okay.
Okay. Thank you.
Okay. So now, now if I consider RO also, right? This we did it in our CS amplifier case also. Then the gain will be GMRD parallel to RO. Okay. So that is it, right? So for each case, when I take a single amplifier, okay, it is VID by 2. Okay, GMRD parallel to R0. So differential voltage is VON minus O2, right? So 2V we get, and then this VID is now we have to for the differential gain amplifier I have to take VID. Okay, so these two get scattered and has to be scattered later on. So finally differential gain should come like this, okay, even if you are taking the half circuit. Okay, so be careful with these 2s and this VIDs by 2. Okay, there are certain examples which are given in the textbook, just go through that. Okay, now what was this? Yeah, that Vin maximum we found out, right, by doing some long derivations. Okay, that can be done in a simplified manner also. Okay, we were trying to find out what will be that maximum voltage for which, okay, output will go to 0, right, and that is the useful range for us. Okay, I can take, okay, VGS1 is equal to VT plus 2 ISS by, because now here the entire current is flowing here. So I have written this equation assuming that, okay, the entire current is flowing here, VG1. Okay, what about VG2? So no current is flowing here. So this has just reached the VT point. So I have written a VT. Now if I take the difference, I get this value, right? What we did earlier, we did a very detailed investigation and we did that derivation, and then we put right, GM is equal to 0 and delta V in, we got this value, right? This was the maximum differential voltage which this differential amplifier could handle, and at that point of time there will be ISS current in one branch and 0 current in the other branch. Okay, and this was one approach which is given in our textbook. This is another approach which you will find in some other textbooks. So this is a relative simple approach. What we have what we did is we are assuming the total current and ISS is flowing here. Okay, so writing the current equation, VGS is equal to VT plus 2 ISS. So the entire current is flowing here to 2 ISS Kn dash. Okay, so this equation we have written. We are assuming no current is flowing here, so it is just reached VT. So I have written VT. So I do the subtraction, I get this voltage again here. Okay, at this voltage, okay, so this will be the there will be no current flowing here, full current will be here. So from delta Vin max is this is from plus this to minus delta Vin. So this is the useful range for a differential amplifier. Okay, so this is another approach of, okay, here we said there is no common mode if both the signals are going high and coming low simultaneously, so that there is the common mode gain is 0. Okay, so and hence the common mode rejection ratio is infinite. Okay, because we have considered an ideal source here. Okay, when this is replaced by a real source, then I will find there is some finite gain also, that we will see it in the next class. Okay, time being, just for the ideal current source, remember that there is no common gain and hence the common mode rejection ratio is infinite, right? Okay, so this is what it says. For the same CMMR is infinite. If both the signals are common, going high and low, then there will be no common mode signal. Okay, so this is common mode input versus signal swing trade-off. Now if the signal is, if I keep the common mode signal very high, right, very high, what happens? As each drain voltage, okay, here it can go, so for this transistor to remain in saturation, you have to cater for, right, VGS minus VD, otherwise this will come out of saturation. So if you increase the common mode voltage, okay, so the overall swing which is available to you will decrease. Correct? Is it understood? So it is better to keep the common voltage here. Okay, if you keep the common volt larger the seam, smaller the swing, because if you keep increasing here, okay, the CM voltage, so you will have to this transistor has to be in saturation, right? For saturation, VDS minus the overdrive voltage should be available between the drain and the source. Since your gate voltage is higher, so that much more VT requires to be catered for here. So your swing will reduce. So so it is better to bias these transistors as close as possible to the to sustain these currents. Okay, we'll see what is the range in the next. Okay, now the common in this particular slide. Okay, what is the maximum voltage here which it can go, right? So if you see here, VDS has to be greater than VGS minus VT for these transistors to be in saturation, right? VGS minus VT. Okay. Now this is what VDD minus I by 2 RD. VDS. VDS.
And I'm still seeing 20.
Pardon? Pardon?
I'm still seeing slide number 26.
The screen is not changing here.
It's not changed. I think because of the net issues, I am working on a mobile. That is the reason. Okay. What is the slide now you are seeing? Is it 28?
27.
27.
Now it's 28.
Yeah,
Now it's 20. Okay. Now if you see here, what is the VDS? Okay. VDS out here is VGS minus VT for this transistor to remain in saturation. So I write VGS minus VT, right? And then so I have VDD minus I by 2. Okay. So this is the condition to be for this transistor to be in saturation, right? So VCM is the common mode voltage which is given here, right? So the overdrive voltage VCM minus VGS minus VT. Okay. So VDD so the what is the overdrive voltage? It is in a VCM I have given here, right? And ID to RD is the voltage which gets dropped across this resistance, okay, as such. So the drain voltage out here will be VDD minus ID2 by RT, right? So now this has to be at least, this voltage has to be at least the overdrive voltage. So I will get VDD minus I2, this is the drain voltage, and this, since this is the overdrive voltage, right? So the maximum voltage you can sustain is threshold voltage out here, right? So this is the maximum. Okay, if I go beyond this, okay, then this transistor will come out of saturation, right? So this is the condition which has to be met, right? VDS is greater than VGS minus VT, right? And what is the drain to source voltage in this case? VDD minus I by 2 RD into RD, right? That is the guy. And what is the source voltage out available out here is common mode minus VGS, right? Common mode minus VGS. So, right, VDS has to be greater than VGS minus VT. This is the condition for saturation. Drain voltage of this transistor is VDD minus I by 2 RD. I is this, so I by 2 RD, and the source voltage is VCM minus VGS, right? So if I from here I get this equation straight away, right? VDD minus I by RD plus VT is greater than or equal to VCM, right? So this is the maximum voltage which I can DC voltage I can operate, VDD minus I by 2 RD plus VT, right? Now how to maximize this, right? How to maximize this? Okay, I can either increase RD, right? If I increase RD, okay, the gain will increase. Okay, if I increase RD, gain will increase, but that will deteriorate my dynamic range out here, right? Because to increase gain, what do? I increase RD, right? RD, if I increase RD, I can get more gain, but if I increase RD, then the maximum common mode voltage which can be given here, okay, will decrease because there is a negative sign out here. So you see the trade-off, clear trade-off between gain and the maximum input range which can be given here from this equation. Is this clear to all of you? Is it okay?
Yeah.
Right? So if I increase RD, the gain, differential gain will increase, okay? But if the differential gain increases, okay, then what happens is the maximum voltage which I can, so the dynamic range out here, input common mode range decreases, okay? Similarly, what is the minimum voltage I can give here? Okay, the minimum voltage is, if the voltage required for this current source for operate is VCS, right? This is minus negative voltage plus that plus VT, okay, plus VT plus V overdrive. What is this overdrive voltage? That is the overdrive voltage required to sustain this I by 2 current, okay, that voltage. So this sets the lower limit of the common mode voltage. This sets the higher limit for the common mode voltage. This sets the lower limit. Is it okay with all of you?
Yes.
Is it okay? Right? And here, and how to increase the upper limit? I have got only one variable parameter, RD and I. Okay. So if I increase, if I decrease either I or RD, both has got a direct relation with gain, because if I decrease I also, GM will decrease. If I decrease RD also, GM will increase. So if I have to increase the common mode range out here, right, I have ID and RD. So this is a compromise which you have to do. Okay, you have to compromise on your gain to increase this upper limit. What about the lower limit? On the lower limit, I said VSS is not controllable. VCS is the minimum voltage required for this current source. VT is also not in my hand. V overdrive. Okay. Now V overdrive is something which I can control by using a larger W by L. Okay, I want to minimize this out. So I have to reduce VOV. So I can use a larger transistor and reduce VOV, required VOV for a given ID. Is it okay? I can use a larger transistor, okay, for a given ID, okay, to reduce VOV. Correct? So, so this is one more design parameter. Okay, to keep VC in minimum, if I want to keep, okay, I have to compromise on the area and use large transistors. So I can do a little bit here. So that is one thing. PMOS differential pair, again you can implement a PMOS differential pair also. So the current source will go on top, okay, and the loads will come in the bottom. Okay. So we do have 5 minutes time, so let me quickly show you some simulations. Because of the net connections at my end, I have lost some time today.
So, just one question. There where you are talking about the common mode, higher common mode with the loss in the gain. So what would be the, can you please recapture the benefits of having a higher common modes?
See, it depends on circuit to circuit. Suppose your input signal, okay, there is a requirement from the circuit that the common mode signal can go from this level to this level, right? In that case, so when the user defines, when a parameter of a differential amplifier is decided by the user, so he would say, I want this differential amplifier to operate linearly within this common mode range. So that becomes as one of the input criteria, design criteria. Okay. So that could come from the previous stage also.
Okay, so that's the criteria, and it doesn't have as such a gain or something.
Yeah,
just that.
To meet that criteria. So in analog design, there will be so many parameters which you will have to satisfy. Okay, input parameters.
Okay.
So accordingly, we are doing. So this is a simple differential amplifier. Okay. So what I have done is I have used a current source. Okay. So when you use a current source, you have this option of this is an active load. Okay. Always tick that. Okay. This is an active load. What happens is if you don't tick that, it will assume that this is an ideal current source, and even if you don't give any voltage out here, it will if I give 100 micro amperes current here, okay, there is no way if these transistors are off also 100 can flow, right? But it will push 100 microamperes because this is an ideal source. So ideal source means come what may, this much current has to flow in this source. So whenever you are taking a current source for in LT spice, there is an option known as, okay, this is an active load. Okay, so please press that. Okay. Now I am trying to find out the gain out here of this differential amplifier. I have given a common mode signal of 0.7 for both here, right, for 0.7 here, and I have given a small differential signal, okay, of 0.5. So 1 millivolt is the differential signal. Half signal I have given here, half signal I have given here. They are out of phase. So if you see here, 180 degree out of phase signal I have mentioned here. So the differential signal is of 10 okay, this is, I have written as 5, right? It should be 0.5, right? Okay, 0.5 milli, 0.5 milli, so this becomes an 1 milli out here, right? So this is the signal. So same arc I have. So let me do an simulation, and let me plot an V out, right? So what I am doing it out here is, okay, let me to visualize it properly. Let me give it as 5 only, and let me change this also as 5. Okay, and I am changing the load current, okay, in steps of, see, set parameter from 100 micro, 200 to in steps of 25 micro. So if I keep increasing the load current, will the gain increase? Anybody? If I increase tail current, will the gain increase? Anybody? Gain will increase, right?
Yes, because
of GM will increase, right? GM is proportional, but the operating point will keep coming down, right? The DC operating point. So that is what we'll be able to see here, right? Now this is the first run. Okay, the top one is 100 micro, so it is moving, this is the, here if you see here, as the current is increasing, okay, the gain has increased, okay, but the operating point is continuously shifting below, because more ID VG drop. So you see here the gain is continuously increasing as you keep increasing the value of the tail current, okay, but the operating point is also moving. So you have to be careful with your design, okay. So this is how a differential amplifier can be implemented. So let me show you one more schematic. Okay, now what I have done is, out here is, I am sweeping the DC bias condition, bias voltage here. So let me take what happens to the output voltage here, right? So if you see here, initially the common mode voltage is 0, right? Here this common mode voltage is 0, so both the transistors are in off. So the output voltage is here will be a VDD. So if you see here, right, so it is VDD. Then as the common mode input voltage is increasing, current is started flowing, and now in this region, if you see in this region, current of ID by 2 will be flowing, and hence you are getting a good gain here. And again, if you keep increasing, the transistor will come out of saturation, and the gain is going high, right? Gain is decreasing. So is this graph understood? What I have done, I am finding out the transient response. I have given this also as a variable. I am slowly sweeping this output voltage. So initially when the common mode signal is not there, so you will find, if I try to plot the current also, let me, so it will become clear. See, initially there is no current, right? And then there is current is established, ID current is established, 50 microampere, right? 100 microampere. That once the 50 microampere current is there, in this region, okay, in this region I have a maximum gain. Here the current is 50, right, but the transistor is coming out of saturation, right, because we have seen the common mode range, right? It can't go beyond that, otherwise the transistor will come out of saturation. So here it is going out of saturation, again the gain is going. So this is the useful range for us, common mode useful range, you can see from this graph. Okay, is it okay with all of you? Yeah, okay, then thanks a lot. We will stop it here. Yeah, tell me.
Hello.
Yeah, tell me.
Sir, even after increasing common mode to high value, why did voltage get limited at here 1.3 millivolts? Sir, in the green curve or in the green curve?
In the
V out is after the settling time at 240 milliseconds. It is not dropping below 1.3 millivolts, right?
Because maximum
Even
current
though-
has reached, right? Maximum current is 50 microampere, right? Here I have set 50 microampere. That is the max 100 microampere. So 50 can flow. So 1.8 minus this. Okay. So that is now. Suppose I put this as instead of 100. Let me put it as 400. Okay. And I do a simulation. Now if you see here, okay, this is coming to very, very low values. It is right. So again there won't be any gain. So you have to accordingly do. So let me put it as just 200. So okay. So if I do the simulation now, see you will find here, right? It is come up to 0.8, right? So accordingly, so these are all the depending on the, if I am putting 200 out here, right? I am so I have to accordingly to cater for those currents. I might have to increase the transistor sizes also. 40. So these are the things which you can try and do and analyze the circuit in a much better manner, right?
And sir, in this simulation, if you plot the if you plot the voltage at the source of the MOSFETs,
okay,
that will also saturate it.
Here,
basically that.
Yeah.
At the source.
Here.
Yes.
So this is the voltage.
So basically it is not increasing more than 1.3 volts.
Yeah, because you have IR drop, right? More current can flow.
Correct, okay.
Yeah. IR drop.
Okay, sir, understood.
Right?
So 1.8 minus 50 into 10 kilo ohms.
Yeah.
59. So
Yeah,
that will limit it to 1.3 volt, and then even if we keep on increasing the gate voltage, then VGS will drop below VT.
Correct.
And then it will come into triode. Okay, sir.
Okay. So these kind of simulations you can do, and further. So this is a very useful tool. What I have done is, just to give you a hint, I have put 0 value initially. Okay, there is something known as PWL out here. At time is equal to 250 milli, I have put a value of 2.5. So this voltage is slowly increasing, and I have for 250 milli I am sweeping this voltage actually. So this is actually time, but in other words it is also voltage. Okay, that much milli. So I have just used that kind of source to bring out this point to you all. Okay, so thanks a lot. We'll end it here. Next class we'll see further about it. Okay, thanks a lot.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Sir, please stop the recording.
Yeah, I have stopped it.
Okay, thank you, sir.
Okay.